I guess we can get started. So plenty of room up front for those who want to move up. Anyway, this is, I'd like to talk today about some recent work we've done in the ODP project to improve the scheduler model that we're supporting. This work was done largely by Bala from Cavium, who was not able to be here, so I am presenting in his stead. Quick disclaimer that this is work in progress, so the final design and APIs shown here may change before they're released as part of ODP. But we would very much like your feedback, so either here or on the ODP mailing list, which is, I've given the address there, so feel free to participate. So quick review of what's the scheduler all about. So scheduling is an alternative to what I think a lot of people are familiar with if you're coming from the DPDK world of polling. The idea behind scheduling is rather than have the application figure out how best to exploit many core environments, have that built into the system so that independent of the number of cores that actually exist, the application can simply structure itself as a series of threads that run in parallel and can receive events that are distributed out to them automatically by the supporting framework. So the scheduler supports automatic scale out of events to threads in many core environments. Events reside on queues that the scheduler is scanning, and queues can be offer both event sequencing as well as context. And the sequencing provided is one of three options: parallel, ordered, or atomic, and we'll go through those in a bit. But the key is that the scheduler is essentially an abstract function, and so whether it's implemented in software or hardware is transparent to the application. This continues the ODP theme of system independence and being able to have applications exploit acceleration features transparently. So if we look at a parallel queue and ordering, if I have a series of events that are on parallel queues, the scheduler will scan those. It will schedule them to run in parallel, hence the name parallel queues, on worker threads, however many are available. And any synchronization needed among these events is the application responsibility. So parallel is sort of the base case where either the application doesn't require any synchronization among events or it has its own method for doing so, in which case we provide that efficient way of doing that. When they're done, these events wind up on the output queue in potentially unpredictable order. If the application hasn't made any special arrangements, there's no way to predict when that'll arrive. Conversely, an atomic queue offers guaranteed synchronization among competing events originating from the same queue. The scheduler will ensure that threads process events in parallel, but no two threads can process events from the same atomic queue at the same time. So no locking is required within the thread itself because the scheduler is guaranteeing atomicity as part of the semantics of the origin queue for those events. And as a result, anything occurring on the output queue is in the order that it appeared in the input queue because it was simply processed as if there was only a single thread operating on that queue at a time. Now, this has the advantage of providing very easy synchronization, but obviously at a loss of any sense of parallelism. And in particularly, if I have the type of work that I'm doing for a packet stream is too much for a single core to handle, the question is, well, how do I deal with that situation? So for that, ODP provides ordered queues, which are a refinement of the atomic model in the sense that we relax the restriction that basically says only a single event from a queue can be processed at a time to allow these events to be processed in parallel. However, the system will perform reordering processing as necessary to guarantee that the events will appear on the output queue in the same order that they occurred on the input queue. And this allows scaling of flows across multiple threads and cores without loss of ordering. So in this case, we see that here we have three. If you look at the purple flow, I guess that sort of shows up as purplish, or maybe it's just black. We have elements 1 and 2 have already been placed on the output queue. 3, 4, and 5 are in process in parallel, and elements 6 and 7 are still awaiting processing. But the point is that no matter which thread finishes its event first, element 3 will be the next one that appears on the output queue. So if element 5 finishes first, then it will actually be held in a reorder buffer, waiting for the preceding events to be processed. So these capabilities working with the structure results in this sort of simplified worker thread structure. I'll do some initialization processing for each thread, and then it basically enters a while loop where it simply asks the scheduler for work, does whatever it needs to do, and then enqueues it to a destination queue to be processed by the next event in the pipeline. The one wrinkle that ordered queues provide is if I have this notion of multiple events that are being processed in parallel, the question is, well, what happens if I really need to do something sequential in the middle of this ordered processing? For instance, in encryption, I may want to assign a sequence number that has to be, in sync. Well, the solution that ODP provides that is what we call ordered locks. And an ordered lock is a special type of lock that exists within an ordered synchronization context that allows a critical section to be defined, which is processed in order, independent of the other parallelism that is going on. So if element number 3 is being processed here and it calls ODP schedule order lock, that call will not return until elements 1 and 2 have already been processed. So that by the time element 3 acquires the lock, we know that it's now being processed in order. So this provides a small ordered serial section within a larger parallel flow. There are, however, some issues with the current ODP scheduler design. And really 2 of them. The first one is a resourcing issue. Synchronization is limited by the total number of queues, and each ODP queue contains a queue context. So if I'm creating millions of queues, that may well result in memory constraints in many environments. Because typically what I wanted to have is supporting lots and lots of flows, but I don't necessarily need context associated with each of those flows. So having a full queue to represent that flow is perhaps overkill. There's also a functional issue, and that is that the flow concept is tied to queues today. And we really want to associate flows with individual packets and allow flow identity to change in response to things like decapsulation, decryption, et cetera, during processing. So how do we do that? What we've been experimenting with now is introducing the notion of lightweight flows, which are similar to an ODP queue, but without the context. The way we do this is we allow events to be assigned specific flow IDs by the application before enqueuing onto a scheduled queue. Event synchronization, whether it be parallel, atomic, or ordered, is then performed at a flow level on that queue rather than at a queue level. So when an event is received from the wire initially, an initial flow ID is generated by the ODP implementation. And we already have a set of classification APIs that allow that to be expressed as to how you identify a given flow. The event flow ID is enforced only, that's interesting. Can we, We're very secure here. Okay. When the event flow ID is enforced only when the event is enqueued to a scheduled queue. And we also are supporting backward compatibility with the existing ODP scheduler. So if you don't care about flow IDs, you don't have to take any special action. You only have to do new things if you want to access these new features. So let's see how this works in practice. So here we have a view of what we would call the flow unaware scheduler, which is sort of the default mode of operation for the scheduler. We have 3 queues with 2 events each, events 1 through 6. In the when we're operating in flow unaware mode, the flow ID is implicit in the queue ID. So essentially, the fact that you're on Q1 means you're part of flow Q1. Okay, if you're on Q2, et cetera. So all events in the same queue belong to the same flow. By contrast, when operating in flow aware mode, each event has an explicit flow ID which controls parallelism within that queue. So here we see the same 6 events, 1, 2, 3, 4, 5, 6 on 3 queues, but now each event can also be tagged with a flow ID. So we see, for instance, in Q1, both events are tagged with flow ID 1. On Q2, we have an event that's tagged for flow ID 1 as well as flow ID 2. And then on Q3, we have 2 events that are tagged for flow 2. So the important thing is that what this allows is queues to support multiple flows concurrently, but it's only within that queue. So the synchronization that's provided, as we saw in the previous slides, is essentially controlled by a combination of the queue ID concatenated to the flow ID. So for instance, in the case of Q2 and Q1, we see we have a packet that's identified as flow 1 on Q2 and packets on, that are part of flow 1 on Q1. The way scheduling will work here is that the scheduling guarantees, parallel ordered atomic, will be provided for the 2 flow 1 events on Q1, but not between flow 1 and flow 1 on Q2. Okay. Whereas in the case of Q2, since flow 1 and flow 2 are separate flows, let's suppose Q2 is an atomic queue. That means that both of those events could be dispatched concurrently because they're part of different flows. Okay, whereas in flow unaware mode, all of the events on Q2 would be treated as part of the same flow and therefore could only have one at a time dispatched. So there's a potential for additional concurrency there. The scheduler modifications for the new, this new APIs are, first of all, we've added an ODP schedule capability API, which allows the application to discover that, yes, we do support flow aware mode and what's the maximum number of flows and the maximum queue count and things like that are supported. There's now an ODP schedule config API, which allows the schedule to be configured to enter flow aware mode or conversely by default be flow unaware. Flow unaware scheduler is basically the same as the existing ODP scheduler. The application configures the number of queues and the flows required. So for instance, if this follows a model that we've adopted over the last few years of the capabilities say what the limits are of the implementation, and then the configuration may say, well, I only need X, you may do Y, but I only need X, which is lower, and that may provide opportunities for the implementation to be a little more efficient. So I can do 1 million flows, you only need 10,000, oh, well, maybe I can do something more intelligent. The important point is that the scheduler configuration has to be done before queue configuration. Since once the scheduler is up and running, then that definition is locked. ODP Schedule Start is a new API that basically says I'm done configuring, so you can start dispatching things. the scheduler configuration cannot be modified after start. We initially thought of having an ODP schedule stop and then being able to reconfigure, but the current thinking is that that's sort of overkill and is not really necessary. That if you're going to be in flow aware mode, you'll do that as part of application initialization, and then you're good for the application. And then finally, there's two APIs, essentially a getter setter for the flow ID attributes for events. So we can get the event flow ID and set the flow ID. And so this results in the following modification to that hypothetical simplified worker thread. Again, we still have the initialization for that thread. We still have a loop where the basic processing is schedule the event to get it from the next event to be processed, do whatever processing I want, and send it on its way. If this was an ordered queue, I can still put ordered locks in there. However, the two new things basically show I can retrieve the current flow ID if I wish, and I can set the flow ID for the next processing stage before I enqueue it. So that's allowing the, for instance, if one of the things that this processing thread was doing was decapsulating that packet and saying, oh, well, now that I see I've stripped off this outer header, which was part of flow A, the inner packet really should be processed as part of flow B. So the expected benefits of this new structure is finer grain control, a better fit for many applications and resource-constrained platform environments, as well as, finally, a better compatibility with the event concepts that are currently being introduced into DPDK. Okay, so one of the things that we've consciously tried to do and have been trying to do is, when possible, have the APIs that ODP is using be consistent with some of the concepts that DPDK is using, so that when we do map the ODP APIs onto DPDK with the faceplate approach that we discussed this morning, that just makes it that much more efficient and direct. So, any questions regarding these changes?
So when you set the event, the flow ID for the next stage of processing, if somebody then does a get event ID, do they get the one that got them there, or do they get the one that you set?
They would get the one that you set, because the well, I mean, first of all, until you release control of that event by calling something, I mean, you still own it, so you could, in theory, you could set it 6 different times before you actually enqueue it. It only matters at the point of enqueue as to what the flow ID is.
But there's only one spot for a flow ID, which means once you set it and you read it later, you get that same flow ID.
Correct.
And what about a concept of, can you have a thing of, well, it's a brand new flow, but I want to do flow processing, but I don't want to give it, I don't know what the flow ID is, because I'm going to create it when I look at the first packet of the flow. So I still want to have the flow, some flow.
Well, flow ID, that's a good point. The flow IDs that we are anticipate is essentially an application designator. So the application manages the flow IDs, except for whatever initial flow ID was assigned, by the system as the packet was originating. Now, there's lots of different ways that you can handle that with conventions over, valid ranges or ones that you're using, et cetera. So it's really up to the application. And actually, I think one of the things we'd be interested in is, if you have some specific use cases which says, hey, this is the sort of shape of the ID struct space that I want to work with, that, since, again, we're still defining these APIs, that's the sort of input that we'd really like. Anything else? Okay, well, thank you very much.